Hello, and welcome to today's webinar, Responsive Tools and Pushy Actors, with Michael Reed, who's a senior software engineer at Gilt Group. My name is Laura Masterson. I'm the community manager here at TypeSafe, and I'll be your host for today's session. This is the first in a three-part webinar series that we're running today that focuses on how TypeSafe technologies are being used to handle the challenges that modern retailers face. So these range from modernizing legacy architectures to effectively managing concurrency. So the other presenters today are going to include New Run. They helped Walmart Canada launch its first responsively designed enterprise e-commerce website. Our partners Tomax are also going to present, and they're going to share how a reactive model helps retailers tackle issues like concurrency and real-time data flow. So I hope you can join us for those. Before I hand things over to Michael, just a few things to note. The webinar is going to be recorded today, so you should receive a link to the recording shortly after we wrap up. Look for those in a day or so. If you have any questions throughout the session, just feel free to insert your questions into the little Q&A box. And either myself or Michael will address those throughout the session, saving a few for the end for a short Q&A. All right, with that, I'm going to hand things over to Michael. Michael, thanks so much for joining us today.
Hi, everybody. Thanks for the introduction, Laura. Really excited to be here and have the opportunity to give this talk. Slight note, I am not going to talk about push notifications. Instead, I'm going to talk about how we manage our inventory at Gilt, because I have more personal knowledge on that subject, and it also faces similar scalability challenges that we're trying to solve using Akka actors. So you've already heard that I'm a senior software engineer at Gilt, and I work on the back office team to give a little bit more detail. Excuse me. So you may or may not be aware, Gilt is an online flash sale site. We sell things at a fairly high discount for rather high-end retail merchandise. And the general way that the site works is that we every day have new sales at noon. So that presents an interesting scalability challenge where we have this sort of peaky graph that has high peaks at noon and high peaks at midnight, since that corresponds roughly to noon in China. So a little bit about Gilt Tech itself. We're about 130 engineers, 200 employees in the tech department in total, split across New York City, Dublin, and Tokyo. We do have some open source stuff over at gilt.github.io that I think we've been a little bit more active on in recent months. And the way we're organized is into small autonomous teams that sort of largely make their own decisions about the individual technologies that they use and what particular projects they choose to work on, within the framework that each team is responsible for driving some key performance indicator or taking charge of some kind of initiative like personalization or email. The back office team is somewhat distinct from the rest of the teams at Gilt in that it's a very large team that's further subdivided into smaller teams that focus on individual aspects of back office, from things like payments, customer transactions, and shipping to inventory management, which is what my team focuses on. So this is a graph of what I alluded to earlier about our traffic peaks. It's a little out of date, actually. The peak on the right actually tends to be higher now because of that noon peak in China that I mentioned. So that graph sort of leads to these interesting scalability challenges where for most of the day traffic on the site is not super high, but we have these big peaks where you have 10 to 100x increase in traffic. And that basically affects almost every system that we build, since a lot of them are ultimately related to the customer experience on the site. So for inventory management, People are putting things in and out of their cart, buying things. There's a lot of changes going on in terms of how many units we have available at any given time. So the stuff that we work on is directly affected by that traffic. One of the things that we've done to sort of help with that issue is we have, as we've done with our teams, we've sort of decentralized our services, split them up a lot, so that we have now hundreds of microservices. And that's sort of how we're structured at Gilt. So we use a lot of different technologies. We started with Ruby and Postgres, and then we sort of branched out to Java to help with some of the scaling issues, and have since moved on to Scala because as an organization we feel a lot more happy and productive using it. And through that we've come into contact with Play and Akka, which we also feel pretty good about. So now I'm going to talk about the sort of history of scaling inventory at Gilt to deal with those peaks that I keep talking about. So the original architecture for our inventory management system was pretty simple. Gilt started out as a Rails app built on top of Postgres. So all the units were created in Postgres. So when we created a sale, we would create all the units we were going to use for the sale up front in Postgres using Rails, basically. And then also when someone wanted to check out, we would create an order for them and attempt to get a unit from the database and validate that we were able to get the unit using database constraints, which, from a correctness standpoint is pretty nice because you're pretty much guaranteed that we're not going to oversell or anything weird like that. But as you start to add more and more users onto that, and you get into the tens of thousands or hundred thousands of users, that doesn't scale very well. And earlier on we had some problems where the site would basically just tip over at noon because Rails would lock up because of all the database contention. So to solve that problem, we switched our reservation model to an in-memory service written in Java that basically tracks all of the units that are currently for sale on the site and makes them available for reservation for a user's cart. So that's a much better model because that's very fast, and you're not really doing any writing to disk or anything crazy like that. And it's also not in Rails. As I think most of you probably know, Java is a lot faster than Rails, so there's benefit there as well. So what that model did not address is performance issues with respect to the actual creation of the inventory, which was still done in increasingly large batches inside of Rails, just directly against the database. So within the last 2 years, we did something to address this because we've been doing more and more things that involve creating hundreds of thousands of units in a day potentially, which is not a great thing to do in Rails. So we decided to pull that out of Rails and put it into Scala. And the way that it works is that we say how much inventory we need to have, and we have a Scala service that incrementally creates more by pulling based on a number of factors, including how many units are currently in the database and how many units we need to have available in the actual reservation service. But, excuse me. So it's fairly fault tolerant. It runs on 4 servers in production, although only one is doing work at any given time, and the others are there for failover. So as you might imagine, it's a bit of a waste of resources if we always have 4 nodes running, but only one ever doing work at any given time. And also, we could handle much more scale if we could leverage all of the servers that we have. So the next step is we want to sort of distribute it and make it less polling intensive so that we're not wasting as many resources doing it. So this is where Akka comes in. We want to create a model that allows us to do event-driven unit creation. We still have these pools of units that are created with upfront quantity limits dictating like the max number of units that we can ever create or sell. But instead of having the application poll the database and reservation service to know when it needs to create units, we just subscribe to various events that tell us when inventory levels are changing or when the pool is changing, because those are the only times that we actually need to do anything. The way that Akka can help with this is that the SKU, which is a stock keeping unit, it's basically if you have a shirt that's black and a medium, that's a SKU. So the unit by which we group inventory into logical groups. So that forms a natural unit of concurrency because as you're creating inventory and giving out reservations, you don't want to be giving them out for the same SKU at the same time because you can exhaust the SKU accidentally. And so we would want to have an actor for each SKU. So the event dispatch runs locally on each node. Each node is capable of receiving events with respect to pool changes. The service exposes an API where users can change the amount of units they want to be available for a given SKU, so events come from there. And then for changes that are coming from the front end by people making reservations or placing orders, we have still a single-threaded process that tracks them because we only need one point of entry from that subsystem, and still with failover, also provided by Akka. So now I'm going to go over some code examples. They're not directly from production, but they're they're basically like building blocks that we would use to build a system like this. So Akka is really nice because you can just pass messages between actors and your state is separated and encapsulated by individual actors. But Akka itself doesn't make any guarantees about reliability, so you sort of have to basically, if you're doing distributed actors, you're not guaranteed that a message from node A is going to reach node B, so you kind of need to take care of that yourself. There's some out-of-the-box solutions that I have linked to in my slides. I'm going to show you how you can quickly sort of create your own very simple one, and then later build on that to do something a little nice that the out-of-the-box solutions can't really do because they don't know necessarily as much about your messages as you do. So we start with a really simple message class. It has an auto-incrementing ID, and you can pass in a body that's whatever you want. In the examples, the body is always going to be just a number. It's simple. So using that, you can create a retrying actor that, given a target to which to send messages, will forward those messages to the target and then keep retrying until it gets a confirmation from the target that it actually received the message. So this is a potential target that actor would be sending messages to. All it does is receive messages and respond with an acknowledgement that it actually got the message, and then print it. Pretty boring, pretty simple, but we'll have more interesting examples of receivers later. And this is how you would combine those two actors together and run them in like one main method. So I see a couple questions in here about whether or not we're using Akka clustering and how we're doing skew actor partitioning across nodes. The answer to the first one is yes, and the answer to the second one is via Akka cluster, which I am going to touch on in the next example. So for the next example, we're going to reuse our simple message, same thing, and we're going to use it to make a very simple sharded actor, which provides the distribution of labor per skew that we want to have in our system using Akka clusters, cluster sharding functionality. So the actor, the way that Akka cluster sharding works is you give it an actor system and you tell it how to create your actor, and it takes care of both, and you also teach it how to route to your actor, basically. And it takes care of actually performing the routing for you and also balancing your actors across nodes based on how many nodes there are and how much is being done on each node. So our shard actor is very simple. It's basically the same thing as our receiving actor from before, but minus the acknowledgements. And then we have a dispatching actor that only needs to run on one node so that it can publish messages to the shards that it receives from whatever client. And then here we have the configuration that you would need to run this and the code that would actually run it. And so this code basically just prints out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 from different shards. So the next thing we're going to do is we're going to go back to the retrying actor with a somewhat more complicated message and look at how you can in keeping track of the messages that you've sent to your target actors, you can be a little bit smart if you're in a situation where your target is very flaky and not acknowledging a lot of your messages. If your messages are communicating some kind of persistent state and just intelligently drop previous messages from the stream and only keep resending the latest one because it contains enough information that you don't need the others. So now we have one more field in our message. Instead of an auto-incrementing ID, the ID is something that's passed in by the client and is assumed to route to something persistent and stateful, like a skew. And you have a sequence number, which indicates the order in which the message was generated and is globally unique. So there's a couple things going on in this one. At the bottom, you have the block where clients pass in data, and the data is turned into the message that's actually sent to the receiver. So the change here from the original retrying, this is basically the same thing as the original retrying actor here. It will save the message in a list of messages for that ID and then dispatch it to the target. And then above this block, it's waiting on an acknowledgement that includes the identifier for the message and the sequence number, which it will then use basically to delete every message lower than that sequence number, and then remove the entry for that ID if the message set is now empty, because we've delivered all the messages we care about delivering. And then in addition to that, there is a task that we called prune that we run every second. You probably would not run this every second in an actual production system, but for the sake of the toy example, not taking too long to run, it uses a second interval. So every second we run prune, and for each of the IDs with outstanding messages, we go through and we figure out what the latest one is. We just look at the max sequence number. We do some statistics, some stupid statistics where we figure out how many messages we're about to throw away. We clear out the buffer, and then we restore the latest message in there and try to send it to the target again. So this is nice because if your network is really congested, or you have some kind of crazy partition scenario going on, you can still keep sending messages, but you're not going to be wasting as much memory holding all of them, because you know that you can throw all of them away if you've structured your events such that the older ones in the sequence don't matter as much as the newer ones. And this is the actor that we send to in this example. It sort of just mimics having a bad connection by rejecting messages with sequence numbers that are lower than this number down here, which is just arbitrarily 5. And then in the case where it does accept it, it logs that it's acknowledging it, records it. We have this countdown latch here that we're using to cause the main process to wait for all the messages to be sent that you'll see later. And then it sends it back to it sends an acknowledgement to the sender as before. And so here's the code that you would use to sort of run this toy example. Excuse me. First thing you do is create your actor system, and you can create your receiver, and then you can create your retrying actor with pruning that will send messages to that, forward messages to that receiver for you, basically. So we have 3 IDs, we run through them, and then we send 5 messages for each. That's 5 is the flake number. The last is the first message that will be accepted by the actor. And then we wait between each one so that there's time for the pruner to actually run. And if you run the example, you can see the output. You get like some neat logging messages about how it's waiting for all these messages to go through, but actually it's pruned out like 4 of them, and it's only waiting for 3 instead of 15. And then at the bottom, we wait so that the JVM doesn't exit before the system has actually run all the code, since everything is running asynchronously. So now we're going to combine the sharding and the pruning. That's really what the pruning is for. And to do that, we just have another main method that creates a clustered actor system, creates a sharded actor using our flaky receiver, and then on the first node that it created, runs the same code from the previous main method to dispatch the messages, then waits again. And that's the end of my slides. So, questions?
Michael, thanks for presenting. While we wait for more questions to come through, would you mind just repeating out loud some of the questions that were submitted earlier? So,
yeah.
For example, there was a question on which version of Play you use at Gilt Group. that was asked by Roman. So maybe just addressing some of those so people can hear them.
Sure. Yeah, so Gilt is on the two most recent actual releases of Play. Some of our older apps are on 2.2, and all of our newer apps are on 2.3, and we're in the process of upgrading some of the older ones. And there's conceivably some Play 2.1 sitting around somewhere but the vast majority of things are on 2.2 or 2.3.
Cool.
Roman also asked about, sorry?
Oh, go ahead. I was just going to repeat the next one, so you go ahead.
Yeah, it looks like Roman also asked about something called eBean ORM. To my knowledge, we do not use that at Gilt, and I have never personally used it. So if you want to know what ORMs we do use, we use Slick. We've used Squirrel, although we're not using it in anything new. We found that the documentation for it is not great, and it does not seem like it is very actively worked upon right now. And we also use ANorm that comes from Play. I personally like ANorm. Well, first off, ANorm is not actually an ORM. The name actually means, I believe, not an ORM, basically. Excuse me, but I really like it. And I think the SQL parsers that come with it make it so that you don't really miss not having an ORM, and it's very nice that you can just write all the crazy SQL queries that you want without having to worry about whether or not the ORM you're using can actually express them. So a question from Dragiza? No, sorry. I answered this earlier, but in case people didn't hear, we do use Akka cluster, although it's not used extremely widely, but I think we're going to be using it more widely in the next year or two as we start building more real production systems with Akka. We do have a couple of push and email systems that are built on top of Akka right now, but they don't actually use Akka clustering. One of them has a static sharding config that's managed independently of Akka. Excuse me. And the other has something similar. To Jan's question about an actor per SKU, it is realistic if you're only considering the set of SKUs that are active at a given time, which is what we care about, the ones that actually have inventory. If we were trying to manage every SKU in memory throughout the history of Gilt, that would probably not be a very good idea. But given 4 nodes, and we don't actually keep a whole lot of state per SKU, it's just some counts, it's pretty manageable memory-wise to have an actor per SKU. To Felipe's question, I do not know of anyone who just uses Akka Remote. We don't really, I believe someone right now is working on one purely Akka-based system, which I think is the only reason you would really want to do that. So we may be using it, I think we'll be using it for that, and we'll see how we like that. To Sunil's question about what version of SBT we are using with Play 2.3, I think most people are using 0.13.5. Our internal SBT plugin actually just stopped supporting SBT versions lower than that. So actually, let me reverse that. I think most people are using 0.13.1, but we're trying to get them to start using 0.13.5. Cesar's question. I will go back to the link for. So Cesar asked if I could go back to the link for the code from the talk. It probably is. Yeah. The example. So this is the URL for it. The examples do run, and I think they're pretty interesting to play around with if you pull down the code and want to look at them. It is. kind of hard to go through them in slides. So to Pradeep's question, at any point, if you are creating an actor for each SKU, how many of them will be created at the beginning of sale and how many during peak periods? So the idea is that we wouldn't be creating them really based off of that necessarily, but if the system already knows about them, the system would already know about them. They'd already exist, and it's really message volume that would be increasing during peak periods. But having the incremental model makes it easier to causes it causes a more stable graph because rather than just having big, huge batches of work to do, we'll be doing the work as the changes are being made. To Dragiza, what do you currently use for service discovery if you are not using Akka clustering? Most of our apps right now use Zookeeper. Akka, one of the reasons Akka is attractive is that Zookeeper is, for other services that are using Zookeeper for coordination, Zookeeper is a centralized system, which potentially represents a point of failure. Whereas for the clustering model as Akka is all peer-to-peer. So as we scale to more and more microservices, we don't have to worry as much about overwhelming our Zookeeper cluster. Nasir, no, we do not persist our events. I don't have any personal experience with Akka persistence. So Jan Borgelin is asking for a high-level architectural slide. I don't have one right now, but I could email you one offline later because we do have a lot of them lying around. So does anyone else have any questions?
Looks like we've gone through all of them. So, Michael, thank you so much for presenting. If more folks do have questions for Michael or anything regarding the webinar, feel free to email them my way. Email is laura.masterson@typesafe.com, and I can make sure that Michael receives them. So again, thanks so much for presenting today, Michael. Really enjoyed it, and we hope everyone joins us for the next 2 sessions on reactive retail and join us for future webinars. Thanks so much.
Thanks. Thanks for the opportunity.